Hey, everybody. So you were supposed to have, for today, made a graph out of your circle data. Now, this is first period's circle data. So if you're not in first period, then these numbers don't look the same as yours because, again, I'm not doing this video 5 different times for 5 different classes. So you'll just have to kind of pretend that this is what your graph should look like because it should be pretty darn close because we were all measuring the same objects. And so we should have really similar looking data from class to class. So there was one data point that looked a little strange here. It turns out it was the softball. And this across measurement here that was listed at 10.75 really should have been 9.7. I checked it. And so that should have been like over here, which brings the data point like right there. I mean, right at the best fit line. So this is a really good best fit, really good set of data, I think. And then so you were supposed to find the slope. So I picked one place here, which was at a grid intersection. Perfect. So I have whole boxes I can deal with here. And then this one was halfway between 1 and 2 on my axis, but then it was on the 5 for the vertical axis. So that's a good point because, again, I can estimate a half a box really easily. And so I did. I said 5, 10, 15, 20, 25, 30, 35, 40, 45, 50, and that's 50 centimeters of rise. And then because I went by ones on the x-axis, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 and a half. So 16.5 centimeters for the run. And so I took, get myself out of the way, I took 50 centimeters for my rise, over 16.5 centimeters for my run, and that gave me about 3.03 for my slope. And we were wondering, okay, what's the unit of measure here? Like, what is the unit of measure for this? Because it's centimeters over centimeters. What do you get when you take the same thing over itself? So something over itself. So what is 5 over 5? Or 10 over 10? Or a million over a million? Anything over itself is what? 1. We say it cancels, right? How many times does 1 go into 1? Once. How many times does 5 go into 5? Once. How many times does a million go into a million? Once. So that means if you have centimeters over centimeters, it's just gone. There's like, I guess you could put centimeters slash centimeters, but what is it? That means it's 3.03 centimeters for every centimeter. That seems kind of strange. 3.03 centimeters for every 1 centimeter. Now, one thing I did is I wrote it out a little differently. I said, what if it's 3.3 centimeters of around for every 1 centimeter of across? Well, that makes more sense. If you add the around and the across to the explanation, well, that makes more sense. So there's about 3 centimeters of across for every 1 centimeter of, oh my gosh, I said it backward. There's about 3 centimeters of around for every 1 centimeter of across. That's what the slope's telling us. It's about a 3-to-1 ratio, which is directly proportional. And the proportion is about a 3-to-1 proportion. Okay. Then you were supposed to write the equation for it. Well, that means you got to look at the y-intercept. And mine is very small. It's way down there near the origin, about 1. I would say that's about 1 centimeter. If I'm going by 5s here, that's far enough down that looks like that might be about 1. So a 3-to-1 rise to run with a 1 centimeter y-intercept. And so my equation then looks like this. Around equals 3.03 times, that's my slope, with no unit because it's centimeters cancel centimeters, and so there's no unit on it, times across plus 1 centimeter. Well, then we needed to look at what does the y-intercept tell us? What does the y-intercept tell us? Well, that tells us that if, because again, there's a statement you were supposed to have written down, and it said that the y-intercept is the value of the y variable when the x variable is 0. So if you have no across, 0 across, 0 times 3 is 0. So for 0 across, we would still have an around measurement of 1 centimeter. Now, does that make a lick of sense? If you have an if you have an across measurement of 0, that means you don't have a circle, because all circles have an around and an across. If you don't have an across, then you don't have an around, or you shouldn't, which means what? Which means this 1 centimeter here, my line, the fact that it doesn't go to the origin, that means that we probably goofed up our measurements. We didn't measure things perfectly. I mean, I don't think that's probably any surprise, right? That we didn't measure perfectly. That's what that's telling us. It's telling us that, hey, you didn't measure perfectly. You shouldn't have a value here for the y-intercept. It should have crossed at the origin, because you can't have an around if you don't have an across. That's just the way circles are. So this is an indication that we probably messed up our measurements. No big surprise. We're human. We're guessing, right? All these are guesses anyway. And then where the data points are guesses. And then where the line is a guess. And then where you pick for your slopes are guesses. So we got a lot of guessing going on here, okay? But I mean, pretty good guesses, because 1 centimeter is still pretty small. I mean, that's close to 0, especially when our graph goes all the way up to like 60. So our biggest value here is 60. 1 is very small compared to that. Okay. Now, our y-intercept isn't always going to be 0, but in this case, it probably should be. Like in the case of the height of the kid, as the kid got older, so as that child was getting older, the height was changing. But the fact that we had a 20 or so inch y-intercept on that graph, that was because that child started at age 0 at a height. The kid didn't come out, 0 inches tall. In this case, if we don't have an across, we shouldn't have an around. That just makes sense, I think. Now, then I started asking everybody, hey, what does this 3 represent? What do you think this 3 means? So then I said, hey, hold on. So what I'm getting at here for the y-intercept is that sometimes we have error, okay? Sometimes we don't measure things perfectly, and that means our line doesn't cross at the origin like it should. And that means there's probably error. Because in this particular case, it makes no sense that you could have no across measurement but still have an around. So that probably means we have error. Now, what is the official mathematical name for the around for a circle? I hope you're thinking the word circumference. And what is the official mathematical name for the across of a circle? Diameter, right? So if we replace the circumference, or the around with circumference and the across with diameter, and just forget about the y-intercept because we shouldn't have one, what do you think the 3 is representing here? The 3, the slopes that you found that were hopefully close to 3. If you didn't find a slope close to 3, then you may have goofed up somehow. Okay. For your slope to be around 3, for this looking equation, circumference equals 3 times diameter, what do you think that 3 represents? What is it in math that has to do with circles that has a value of around 3? Oh, I may have given it away. Look at this. There's a pi sitting over here. Normally we see it C equals 2 pi r. Circumference is 2 pi r. Well, what's 2 times r? Diameter. Oh, pi times diameter is circumference. So what we just found out, what we just did here, by collecting some data about circles to find out what the relationship is between circumference and diameter, what is the relationship? It's pi. Pi is the relationship between circumference and diameter. It's pi. How many diameters does it take to go around a circle? It takes pi of them. That's what pi is. That means like somebody had to figure this out at some point. Okay. Someone somewhere along the line decided, hey, circles interest me. They're unusual. And they thought, what things can you measure about circles? Well, they have an across and they have an around. And so they did this. Someone did this. And they found out that the relationship between circumference and diameter is pi. It's constant. Every circle, regardless of how big or how small the circle is, there will be pi diameters around it. Every time. That's what they found. And that's what you just found. Okay? This is how physics works. When we're trying to figure out what the relationship is between different variables, we need to collect the data and then look at a graph like this, and the equation that we write out, the y equals mx plus b that we write out, is going to tell us what the relationship is between the variables. And so that's that. So we finished this conversation. Then we started talking about like some real legit observations. And I have this thing here called the Tumble Buggy, okay? And it has an on-off switch. And what I did was I turned it on, I sat it on the track, and it went, and then we observed. We made observations. And this is what the page looked like of our observations. We had observations that looked like this. And it was kind of a mess. And we made a bunch of different observations. And I guess I can get myself out of the way here, off to the side. Oh, geez. Oh, man. There we go. Off to the side. So we made a bunch of observations here. All right. It moves. Yeah. There's an on-off switch. Red flashing light. Yeah. There's no reverse. It's red. Yes. It has 4 wheels, and it's also all-wheel drive. It's battery powered. It has a motor, obviously. And so we made this whole big old list. And then I said, hey, we have to have 2 filter questions. There's 2 questions that have to be able to be answered about the things on this list. And these were the filter questions. Number 1, can it be measured easily? Is it something that we can measure easily? Number 2, can we change it without breaking something? Can you change it without breaking something? Now, I had then asked the class, hey, what do you think these filter questions and our observations, what do you think we're actually looking for? The fact that I have to say, can it be changed without breaking something? What do you think that is we're looking for? What kinds of things change? Variables. Variables change. They vary, right? They're variables. So we're looking for things that change that we can measure about this thing that we saw, this tumble buggy that was rolling across the track. And this is the list we came up with. Now, it moves. After some discussion, during some discussion, we figured out, hey, the fact that it moves means it's changing its position. Its position is changing. Can you measure position? Yes, easily. With what? A meter stick. Does position change without breaking the thing? Yes, that's what it does. Its position changes because that's what the tumble buggy does. It moves. Okay. Then we start looking at the rest of the list, and somebody said constant pace. And so, well, yeah, it looked like it was a pretty steady go of it. And then so we said, well, how can you even tell that? And they were talking about time. Oh, so time can be measured as well. Does time change without breaking it? Well, yeah, time changes for everybody all the time. All the time. You can't stop time. It just goes. So can you measure how long it took to get to certain positions? Oh, now we may be onto something. So we can mark out some positions maybe and then measure how long it takes to get to those positions. And that could be, it sounds like we have 2 variables. How many variables can you put on a line graph? 2. Oh, look at this. We have 2 variables. And so what we decided is that we will collect some data on the tumble buggy, and it will be position data and it will be time data. And so we'll have a position time data table, and then we will plot those points, and then we will see what is the relationship between position and time. That now becomes our question. What is the relationship between position and time? And that's what will happen next time. So the next class we have, you will be collecting the data that we were just kind of talking about and laying it out here. And this is what the graph should look like. All this stuff should be written in your notes. These are the things that we did and observed, the filter questions that we have, how the graph's going to be set up. So position will be on the y-axis, time will be on the x-axis. That's how it's going to be set up for everybody, so we can compare apples to apples when we look at each other's graphs. And then you'll be collecting the data on the next class that we have. So hopefully that makes sense. You don't have anything to do necessarily for the weekend. Just make sure that by the time you come back here, we are ready to collect some data. So take care of yourselves. Have a good weekend, and I will see you hopefully soon.